And welcome back to another lecture of Statistics 479 Time Series Analysis. In today's lecture, we're going to actually do some real statistics with spectral methods. And we're going to try to estimate the spectral density function. And it turns out we've already done it. The answer is the periodogram, and we'll find out more details in today's lecture. All right, so in today's lecture, we have to talk about statistics, specifically for the spectral density, because in the last lecture, we spent a lot of time looking at the spectral density, but we did it from a mathematical perspective. Fire truck. Anyway, we studied the spectral density mathematically, but nobody ever just hands you a spectral density. They hand you data, and you have to figure out what the spectral density is. And we're going to look into that. We're going to talk about spectral ANOVA, which is the spectral version of analysis of variance. And we're going to look at confidence intervals for the spectral density. A lot of good topics today. So let's get into it as soon as I find my way back to my office. And welcome back to another lecture of Statistics 479 Time Series Analysis. Today we're going to continue our discussion of spectral methods for time series, and specifically we're going to look at spectral statistics, right? Because so far most of what we've done is just consider some hypothetical process xt. Maybe it's an ARMA process, maybe it's not. As long as it's stationary, I guess we're good. Like a periodic process, for example. And what we did was we thought, well, we can compute things like the spectral density or the spectral distribution. We can look at the periodogram in some hypothetical sense, but ultimately, if we have data, we're going to want to compute this for our actual data, right? We never really get a mathematical model of a time series in our hands. We get time series data, and we have to know how to analyze that. So what we'll be talking about today is things like how to, well, what happened when you actually compute a periodogram from real data that isn't just an infinite stochastic process, but a finite amount of data, how we can use that to estimate the spectral density. And then also we can look at a theorem at the end that will tell us kind of how good our estimate is in the sense of like a central limit type theorem, right? Because ultimately we can try to get some confidence bands and also do some statistical hypothesis testing to determine if there's a significant frequency in our spectrum, I guess. All right, well, anyway, let's jump into the notes and let's see what this is all about. All right, so we are on lecture 20, and this is spectral statistics. And there's a lot of different topics that we can discuss in the realm of statistics for spectral methods. So we'll cover some of them today. We'll probably do another lecture on this in the next, I guess, follow-up in number 21. But for today, let's go back to what we started with before, which is the idea of a discrete Fourier transform. So given, we'll say data, a time series data, x1 through xt. Basically, we can Fourier transform, do a DFT, a discrete Fourier transform, kind of like we talked about before. And in this case, what we end up with is d omega j is equal to 1 over root t. Again, sometimes the scaling out front can change depending on what textbook you're reading or what computer package you're using, but this is what they're going to use here. And we get our xt, our data, and we multiply by the complex exponential e to the 2 pi I omega j t. All right, so that's our discrete Fourier transform. We've seen that before, and this is for, not t, for omega j being j divided by capital T. So these are all the different frequencies that we can, in some sense, try to detect in our data. If we have t data points, we can have, the bigger t is basically the finer partitioned the frequencies are. Now, we can break this into two separate pieces, right? Because a complex exponential is actually a cosine and a sine, right? There's going to be a real part corresponding to the cosine, an imaginary part corresponding to the sine. So instead of the DFT, we can also consider the cosine transform. Which is simply just the same thing as above. In this case, I'll write it as d sub c to correspond to the cosine. And we're going to have everything the same with the scaling coefficient, with t going from 1 to capital T, xt. But now I'm going to replace the complex exponential with the cosine. The cosine of 2 pi, no I in this case. The I has kind of vanished as we move from the complex exponential to the trig functions, right? Omega j t. And similarly, we also have the sine transform. And the sine transform is exactly what you'd probably expect. It's going to be the same formula, but I'm going to flip the cosine with the sine. And we get something that looks like this. Sine 2 pi omega jt. Okay, great. And if we really want to, what we can do is we can note that the discrete Fourier transform, that is the whole thing, d omega j in this case, can be written as d sub c omega j minus I d sub s omega j. Just going back to the idea that a complex exponential can be written in terms of, well, trig functions cosine plus or minus I sine, depending on, in this case, it's a minus sign, so we get a minus I sine transform. Okay, so we have that, and we're just going to try to get these all written down so we can use them in what's to come. Right, we need that. We need the two transforms. We also need to note the inverse DFT. So the inverse discrete Fourier transform. Remember, Fourier transforms kind of is just a linear transformation. So I can always, well, linear transformations are not necessarily invertible. This one is we can invert it. So in general, you can't always invert things, but in this case, you can, and we can recover the data from the discrete Fourier transform by just summing j from 0 to capital T minus 1 of d omega j times e to the 2 pi I omega jt. In this case, right, we don't have, this is omega sub j, just to make sure that's clear, since there it is, omega sub j times t. And here we don't have a minus sign, again, because it's the inverse transform. Sometimes you see the transform written without the minus sign and the inverse with the minus sign. There's a little bit of ambiguity there, but as long as you're kind of consistent working through it, and you know that sometimes you'll see authors define things slightly differently, it's always good to be aware of that. Anyway, this is basically for all t from 1 to capital T. So all we're saying is that we can invert our transform. We can take our data, create the discrete Fourier transform of it, and then if we want, we can go right back. We can take the DFT, turn it back into our time series data. So they're equivalent in some sense. And from here, we got the periodogram, which we talked about, I think, 2 lectures ago. The periodogram for a given frequency omega j is going to be the squared magnitude of the discrete Fourier transform at that frequency omega j. But if we use the sine and cosine transform, we can write it just as a squared sum. Now these are real, that is, the cosine and the sine transform are real numbers, so I can drop the modulus or the absolute value sign there, the bars that are on either side, right? And I can just say it's the sum of the squared cosine transform plus the squared sine transform. All right, so this is all kind of follows from complex numbers, I guess. But now what we're going to do is we're going to go look at the periodogram a little bit closer, right? Because ultimately we're plugging data in there. So we're estimating, in some sense, the periodogram. And I want to understand what it is that we're estimating when we plug data in. So first of all, yeah, we're going to center it. So next, we center the DFT for j not equal to 0. And what we end up with is that we get d omega j 1 over the square root of t times the sum t from 1 to capital T. And here we're going to say xt minus x bar. And this is e to the minus 2 pi I omega sub j t. Now, this works, and you're probably maybe wondering to yourself, well, why did I specify that j can't be 0? Well, the idea here is that basically, why is this true? Well, for j not equal to 0, the sum of all these complex exponentials, e to the minus 2 pi I omega j_t, just so happens to be 0. Now you can kind of imagine this. Well, let's see. What's the best way to do this? I guess 2 pi omega j is going to give us some fraction of the unit circle, and t is just going to kind of walk around it. So in a sense, this is probably not the best picture, but we're going to do it anyway. If you imagine that all of these complex exponentials lie somewhere on the unit circle, then what it's like saying is we're going to take this point and add this point and add this point and add this point and add the antipodal points, which I'm messing up here a little bit, but the point is that when I add two antipodal points together, I get 0. So by the symmetry of the whole thing, if I sum up all the complex exponentials here, I just get 0, which means I can add and subtract a constant and nothing changes for my DFT. Now, I have to have j not equal to 0, because if j is equal to 0, omega j, I'll just write that out. Right, for j equal to 0, omega j is equal to 0, and e to the minus 2 pi I omega j_t is just equal to 1. And if I sum up 1 a bunch of times, I'm going to get t. So it doesn't work in that case, but in all other cases, we can center it. And that's going to be good, because if we center everything, we're going to get something, well, it's going to be the autocovariant. That's the spoiler, but you'll see in a second where I'm going with this. Basically, the point is that then the periodogram becomes what? Well, it becomes I of omega j, and that is going to equal, in this case, again, it's the squared modulus of the discrete Fourier transform. So I'm just going to use this new centered discrete Fourier transform. I say new, but it's the exact same thing, because like I said, for j not equal to 0, this thing is equal to the regular discrete Fourier transform, because I can always add and subtract a constant inside that parentheses without changing anything. Anyway, I'm going to use the new way of writing the discrete Fourier transform within this equation. And okay, so we get something that looks like this: minus 2 pi I omega j t. Yeah, as I've said before, apart from other stats classes, time series has lots of equations and lots of that you have to kind of fight through. Well, anyway, I can square this whole thing. All right, so what we're going to do, right, is we're going to square the inside of this whole thing, I mean, the 1 over t is just 1 over t. And when I square a sum, what I end up with is a double sum. Here I'm going to take t from little t from 1 to capital T and little s from 1 to capital T. And we're going to multiply two things together here, which is going to be xt minus x bar, xs minus x bar, and then we're going to have e to the minus 2 pi I omega j t minus s all in here. All right, so now things are starting to look a little bit familiar, right? I have the sum of, well, a product of xt minus x bar times xs minus x bar. Well, if we rewrite this a little bit, what we end up with is something that's going to be, well, 1 over t still there. Then what I want to do is I want to change the way I'm writing this summation a bit. We're going to switch to take h, which is kind of loaded notation because we always used h to be a lag. And we're going to run this from minus capital T plus 1 to plus capital T minus 1. And we're going to take out that complex exponential, which is going to be minus 2 pi I omega j. And now what we're going to do is we're going to change t minus s to be h. So what we're doing here is we're doing a there it is. We're doing a substitution, basically. We're going to replace, when we go from between the previous line to this line, we're going to replace, what is it? I guess we want s to become t minus h. So that what ends up happening is that we now have the sum over all the h's, and we're also going to sum, hopefully we get all these things correct here, t from 1 to capital T minus the absolute value of h, because h could be negative or it could be positive. And what we're doing is we're summing, well, the x's, xt plus h minus x bar, xt minus x bar. I think it's supposed to be plus h. No, s is supposed to be plus h. There it is. T plus h. Okay, that makes more sense, I think. Up to a minus sign, which won't really matter in the end. I think we've more or less got it, right? Because ultimately what I'm trying to get at is that when I combine all these things, I end up with the estimated auto covariance. So this ends up just being, if I take this guy and I take the 1 over t out front, then that is just our estimated auto covariance at a lag of h. So what I end up with is just the sum, in this case, h from minus t plus 1 to t minus 1 of k hat h sub x, I guess, because this is, the auto covariance for the time series process x, or the estimated auto covariance. And then I have my complex exponential e to the minus 2 pi I omega j h here, as before. All right, so we now have our, I think we have everything we need, right? Yes, and there's actually one other subtle point that I didn't note before, and that's that we can actually drop the absolute value sign. What I mean by I didn't note before is that I don't recall mentioning this in the last lecture when we looked at a sum like this. So then the question is, well, why am I dropping the absolute value sign? And the reason is because k hat, and I forgot to put the x there. Not super important, but always good to remember that. Anyway, we know that this is symmetric, right? It's an even function. And if I take the Fourier transform of an even function, it's going to be real valued, right? Because if we kind of work our way through this, we would have something that would look like, well, for h, we would have k hat x h, which in this case is going to be, oh, not equals, times the cosine of 2 pi omega j h minus I sine 2 pi omega j h. But then we would also have a term that looks like k hat at minus h. And when I use minus h, well, the cosine, first of all, I mean, the autocovariance is an even function, so I can just get rid of that minus sign. But what I'll end up with is a minus, well, I'm just going to skip that and just say the cosine is even, therefore we still just get a 2 pi omega j h. Now sine is odd, so I get a plus I sine 2 pi omega j h. And what's neat is that when I add these together, what I end up with is just, well, the autocovariance times 2 at lag h times the cosine. So it turns out that we're actually just doing a cosine transform because all of the sine pieces cancel out. So this thing, if we kind of follow this down the rabbit hole one step further, let's go down here. This is actually going to be a cosine transform of the autocovariance function. K, X, H, cosine 2 pi omega j h. And I think I haven't lost any terms, hopefully. Oh, and I guess technically there's there's no 2 in front of this because I'm summing both the positive and negative indices here, h from minus t plus 1 to plus t minus 1. Cool, so there's a couple things to note here. The first is this formula, well, maybe not the cosine transform, but this formula here looks kind of familiar, right? Didn't we just see this in the last lecture? Right? What I'll say is, I'm going to do this in green, from last time, the Wiener-Khinchin theorem number 2 says that the spectral density fx omega is equal to the sum. In this case, I think it was h for, I'll just double check it. I think we're going from plus or minus infinity because we're working in the sort of math world where we can just, take our autocovariance here from minus infinity to plus infinity of kx omega times the complex exponential e to the minus 2 pi I omega h. And this is assuming, of course, as before, that our kx, our autocovariance, is absolutely summable. That is, if I sum from minus infinity to plus infinity of the absolute value of the autocovariance, I get something finite. So the point is that here in green, we're in math world. And up here in black, I guess, we're in stats world. And what it tells us is that, there we are. So the conclusion here is that the periodogram is an estimator, say, for the spectral density, assuming the spectral density exists, of course, and all that. So that's kind of neat, right? It means that we computed this periodogram 2 lectures ago. We computed the spectral density last lecture, and what we find is that they're actually kind of the same thing, but the periodogram here is living in our stats world where we are estimating the autocovariance, and the spectral density is more of a I guess it's a mathematical object in the sense that we're just taking some sense the true autocovariance function, and we're doing a complete Fourier transform of it, h from minus infinity to plus infinity, which you can never do with real data. Yes, and there's one other thing that I have to mention before we move on to the next section, and that's that there's, well, 2 things going on here. One is that we would never have infinite data, so we can't really compute the true spectral density from a finite set of time series data. But furthermore, we also don't really want to sum this far out, because if you recall from like the second lecture in the course, what I said was that, okay, we can compute the spectral, not the spectral density, we can compute the autocovariance function for any lag, but we can estimate it. We can estimate the autocovariance function for any lag, but when the lag gets really big, our estimator becomes bad because there's fewer data points to use. So the note is that kxh of x is a poor estimator for large h. So instead, we should use our periodogram, omega j, I guess it was that I was using. Yes, omega j is going to be the sum, in this case, h from, let's say, minus m to plus m of k hat x h cosine. I'll just do the cosine version because it's the one at the top of the screen, but I could also write the complex exponential if I wanted to. So instead, our periodogram will look something like this for some choice of m, which is going to be much less than t, so that we can get a good estimate of all of the autocovariances. Right now, what should we choose for m? Well, I don't have a good answer for that. I assume that somewhere in the R packages that compute these things, they probably have their own built-in choices for how they actually do all of this. But in our case, it's just good to note that, well, what are we taking away from this? We're taking away that our periodogram is estimated from the data, and the periodogram is an estimator for the spectral density. But we have to account for the fact that we only have a finite amount of data, and that these autocovariance estimates start to become a bit untrustworthy, say, as h gets bigger, because we have fewer data points to estimate it with. Right? When we estimate the autocovariance for a stationary process, we basically take a window or 2 data points of distance h apart from each other, and we slide that along the data. If h is really big, there's a lot less sliding we can do versus if h is small. So just good things to remember. Okay, the next topic in spectral statistics we're going to talk about is spectral ANOVA. All right, so you've probably seen ANOVA, whether or not you've taken a course in design of experiments. You can check out my other course of design of my other lecture course right now on design of experiments, which is also being uploaded to the same YouTube channel. But assuming you don't want to sit through, many hours of that, we're not really doing design of experiments. We're just doing ANOVA here. And I'm imagine that you have seen ANOVA in a past course in statistics, say 101 or 102. Typically, when we do ANOVA, right, we're talking about the analysis of variance. And what we're doing is we're taking the variation in our data and we're breaking it into pieces. So typically in ANOVA, you would have, say, a treatment that you're applying, and you might have some errors or residuals. That would be the simplest one-way ANOVA setting. So we take our total sum of squares, which is like the total variation in the observed data, and we break it into two pieces, the piece that's coming from the treatment and the piece that isn't, which would be the errors. So we would have our two pieces, our treatment sum of squares and our error sum of squares. And depending on the sizes of those two objects and their respective degrees of freedom, of course, we can determine whether or not the treatment we have is significant with respect to the collected data. Now, in the case of spectral methods for time series, it's going to turn out that there's a very natural way to think of this as an ANOVA problem. Of course, we're not going to actually want to use ANOVA methods on this because ANOVA methods would solve a giant linear system of equations, which is not what we want to do in this case. We'd want to use like a fast Fourier transform, but mathematically or and stuff, it's the same idea. So that's why we're going to write this out. So maybe I'll put a little warning here. Don't actually do this. Use FFT instead. I should say don't actually do this with real data when you could just use a fast Fourier transform. But we can still write out our equation as we can still write this out as a giant linear model like we did back 2 lectures ago. So we can take our data xt and we can assume that we have some giant trigonometric expression that will fit our data. T minus 1 over 2, and then we have some crazy thing here, which is going to look like beta j1 cosine 2 pi t j over capital T, to switch to that notation just to have that like we did 2 lectures ago. And then we'll have a beta j2 sine 2 pi t j over t. Right, so we had that big thing, and I said, okay, 2 lectures ago, and this is also assume capital T is odd for simplicity, because otherwise I'm going to have that extra term floating around and it's just going to be annoying, and it doesn't really matter for this what we're doing here. So we'll just assume T is odd so I don't have to keep that extra term floating around. Anyway, 2 lectures ago, what we saw was that we can actually estimate the beta parameters here using least squares regression. Again, we don't actually want to do that in practice because if T is big, we'd be solving some giant system of equations. That would be very sad for a computer to do. Instead, we could use an FFT. But mathematically, I can write it down with no trouble and find out that it's just going to be, well, the sum of the, in some sense, the dot product of the data vector x with the cosine vector cosine 2 pi t j, or I'll do the little j over t here like I was writing before, just to emphasize that j and t and capital T are kind of linked, right? Well, this is just 2 over the square root of t times the discrete cosine transform at omega j. Cool. And similarly, we get the exact same thing for the beta j2s, which is going to look the same, but it's going to be a sine transform, which we'll write out just for completeness sake. T, D. All right. So we have those 2 pieces now. And yes, what else? Oh, yes. And I guess we had one other thing we have to write down, which is the intercept term is just x bar. So not that exciting, but included just for the sake of completeness. So again, 2 lectures ago, we talked about this, that in some sense, we can think of our process xt as we can fit precisely to it having a saturated model in terms of cosines and sines because they form an orthogonal basis. Now, when we do that, we can use least squares and we can calculate the coefficients that would recreate our data exactly. And again, these coefficients are really just dot products between the data vector and either a cosine or a sine vector. I mean, all of linear regression is just like dot products and linear algebra, right? Anyway, the point is that therefore, what we can do is we could actually write xt minus x bar equal to, well, I'm just going to add these things together, but it's going to look like 2 over the square root of t, the sum j from 1 to capital T minus 1 divided by 2, discrete cosine transform at omega j times the cosine 2 pi t j over 2, and then we're going to have discrete sine transform sine, that is the sine of 2 pi t j over capital T. All right. So what is all this leading to? Well, it's leading to the idea that I can square and sum this thing. So if I were to square it, xt minus x bar squared, and sum it for all t from 1 to capital T. So across, so this is a total sum of squares, like we would see in ANOVA on the left-hand side. In fact, it is the total sum of squares of our data set, even though our data set is a time series and not some type of designed experiment like we would typically see when we look at ANOVA. Well, when I square and sum up the right-hand side, what happens? Well, what happens is that, well, I'll just write down the answer, which is we get a 2. I should check to make sure that's not a 4. I could see me making that typo when I wrote this out, but it's not that important for the conclusion. So it turns out that most things kind of disappear here, and we end up with omega j squared ds omega j squared, which can also be written as 2 times the sum j from 1 to 2 minus 1 over 2 times the periodogram, which I think, no, that's written correctly. The periodogram is the squared modulus of the DFT. So I don't need, I was thinking, do I need to square this thing again? And I'm like, no, it's inherently squared because this thing I is equal to the squared modulus of d omega j. It's always trying to keep track of all this notation can be a little bit tricky, right? Anyway, the point, and also you might wonder, like, where did everything go? Well, here what happens is if you imagine the steps that I skipped, I squared this summation here, and what ends up happening is you get a bunch of cosine squareds, cosine times cosines, cosine times sine, sine times sines, and so on. And they all kind of turn into, well, either the coefficients like t or root t over 2. That's right, that's where the 2 goes. Or they vanish and go to 0 in the case that we don't have everything squared up. This was from, if you recall, I think 2 lectures ago, I copied over that giant page of formulas that was just like sums of cosines and sines, and they basically are all 0 because they're all orthogonal to each other. That's what's happening here, that I'm not showing the steps because it's tedious and not overly enlightening in my opinion. But roughly the idea is that the cosines and the sines are basically orthogonal to each other. So every cross term sums up to 0. And the only ones that don't sum to 0 is when I square the ones that correspond to squaring the cosine transform and the sine transform, and then the coefficients cancel out. So that's the hand wave. The point I'm trying to get at here is that we've decomposed a total sum of squares into a sum of the, let's say, frequency omega j sum of squares. So in a sense, this is really the same idea as a nova. In a nova, like I said before, just to repeat myself, we have a total variation or total sum of squares in our data, and we're breaking it into pieces. The piece coming from the treatment, the piece coming from the errors. Maybe we have more than one treatment in our design, then we might have the variation with treatment 1, the variation with treatment 2, and then the errors, the unexplained variation or the errors. In this case, what we're basically saying is I have the total sum of squares for my data, which is in some sense a measurement, a quantity of variation in our data. And what we're doing is we're decomposing it into a bunch of variations attributed to each frequency omega j. So now I have a ton of different frequencies because T is probably large, and I can see how much of the variation in our data is due to each individual frequency. If they're all about equally weighted, we're probably in kind of like a white noise case. If we see some imbalance, then we might be able to detect some prominent frequencies in our signal, in our data here. And we actually can think of this even a little bit more precisely in the sense that, so at the end, I'll say if we wanted to, we could treat each 2I omega j as a sum of squares with 2 degrees of freedom associated with it. And when we add them all up, we end up back with the total sum of squares, which is going to have T minus 1 degrees of freedom. But as I mentioned, we don't want to actually do this. Now, in some R code, which I'll show you maybe in the next lecture, I did do this by hand, and it is kind of neat. You can do it. But typically, if you're going to do this for all possible frequencies, you're not going to want to use the AOV function in R. You're going to want to use a fast Fourier transform. They're doing the same thing, basically, but the FFT is much more efficient than whatever AOV does. Now that I think about it, I'm not sure what AOV does, because the AOV function fits in an analysis of variance model. But if you had a large factorial experiment, you could have a pretty big system of equations that you would have to solve. And there are more efficient ways to do that, like the Yates method, rather than just brute forcing it with like a big system of equations, which is also kind of related to the Fourier transform. So all these different things are together, but hopefully the R functions know what they're doing and we don't have to worry too much about it. All right, what's next? So next we have to talk about what the next section is called large sample behavior. Basically, the idea is we can estimate fx omega by I omega, right? The spectral density by the periodogram. And the question is, how good is that, right? How good is that estimate? and based on my data size, because very often in statistics, we work asymptotically. We think to ourselves, okay, as the data size gets bigger, I get a better estimate of the thing I'm trying to estimate, in the sense that the confidence interval, the confidence band around it, goes to zero. The variance of my estimate goes to zero, and I get a pretty good guess at what the underlying truth is, the thing that I'm trying to estimate. So once again, if we're trying to estimate the spectral density, well, how good of an estimator is the periodogram? And that's what we're going to do next. All right, so in this section, as usual, so we assume, or we don't really have to assume, we just take xt to be a stationary process with mean mu. So we'll have a non-zero, potentially non-zero mean in this case, just because, why not? We've been kind of, I like to be lazy and just assume the mean is zero all the time, but in this case, we can try and do it differently. Now, what we'll have is I should also say with mean mu and absolutely summable autocovariance kxh, so that fx omega exists, which is the spectral density for the process. All right, so now we have all our pieces in place. Oh yes, and what we're going to do is I'm going to say, to make things easier, we will write the periodogram using mu instead of x bar. Now, in the real world, we wouldn't have the true mean mu, we would have x bar. If the data size is big, x bar is going to be really close to mu, and if we mathematically try to work with x bar, it's annoying because we have to consider the fact that it's a random variable. So if we're doing things like expectations and whatnot, we got to deal with that. And there's a little bit of a headache there. If we just use mu as the parameter, the fixed non-Bayesian, right? We're treating mu as a fixed, not random parameter mu. Then we don't have to worry about that headache. So for this section, we're just going to, take the easy way out and replace x bar with mu. If we really wanted to, we could go back and fix it, but for the sake of the exposition here, it's not going to make any real difference, except that dragging x bar around will make everything a little bit more tedious. Anyway, I'm going to write this out as we did. This is a minus t minus 1. I'm going to write this out as we did before. 2 pi I omega j h, and the sum, now t from 1 to capital T minus h of x t, plus h minus mu instead of x bar at this point, x t minus mu. Okay, so this is the periodogram, only I'm using the same formula that we had found above when we were trying to show that the periodogram is closely related to, the autocovariance and the spectral density. The reason I'm writing it like this is so that I can take an expectation of it. If I take the expected value of the periodogram, what do I get? Well, what I end up doing is I end up taking the expected value of, well, most of this stuff is not random, right? So I end up with t, I end up with my sum over h here, which I'm not going to rewrite the indices because it's annoying, and I'm going to have to write another time in the next line anyway. Anyway, I just have to take the expected value. In fact, I can even bring it, yeah, I guess within this sum, but I don't need to bring it within this sum because yeah, no, I definitely don't, because I want this to be the auto covariance. T plus h minus mu x t minus mu. All right. So again, expectation is linear. I can bring it with this complex exponential is not a random variable, so it doesn't affect our expectation. When I take the expected value of this sum, what I end up with is t minus h times the auto covariant. I guess I am kind of taking the expected value of the inside, because the expected value of this thing, maybe I will flip it, just because I think it'll explain more where the next formula comes from. Again, expectation is linear, so I can just bring the expectation inside both summations. Now, the expected value here is just going to be kx at lag h, the autocovariance. And I'm going to sum this thing up, t minus h times. It's not changing. It's the same thing. There's no, remember, it's stationary, so little t does not play in to the autocovariance anymore. Once I take the expected value, there's nothing really happening with little t. So what I end up with is actually a capital T minus h, which is the number of terms in that inner sum, divided by t, which is the t from out front here. And then I sum over all h from minus t plus 1 to t plus 1 of k. Oh, no hat, because I took an expected value. So now we're not dealing with the estimated autocovariance. We're dealing with the true autocovariance. It's always good to keep track of all those things. Okay, so we get something that looks like that. All right, so what are we going to do? Well, we want to know what happens as the sample gets big, right? Because that's what we said. We're doing large sample behavior. So what happens when t goes to infinity? Well, okay, our summation indices go to plus or minus infinity, and the thing out front tends to 1 because t minus h over t will tend to 1 as t goes to infinity. But we actually have to do one other little tricky thing, and that's to figure out what happens with the frequency, right? Because there's a t hiding in our frequency here. Omega j is going to be j over t. So it's a little bit more complicated than you think at first. You want it just to become the spectral density, and that's what it's going to become, but we have to be a little bit more careful mathematically than just replacing t with infinity. So the point is, we also need a sequence of omega j t's such that omega j capital T tends to some fixed omega as t goes to infinity. So, for example, what you might have is, well, omega 1, 2 is 1/2. Omega 1, 4 is 1/4. Omega 3, 8 is equal to 3/8, and then say 5/16 and something like that. So omega, well, I'll just write it all out like I have the example. We could do 5/16. We could do omega 11 over 32 is equal to 11 over 32, etc. So in this case, we'd be tending towards some omega, which is 1/3. So this is just an example that as the sample size increases by a factor, doubles, that is, as I double the sample size from 2 to 4 to 8 to 16 to 32, I can get a sequence of omegas that tends towards some target, like 1/3. The point being here that, again, if I want to take t to infinity in this expression here, then I need to figure out what happens to omega, not just what happens to t, because capital T is hidden within omega as well. Anyway, the point is that in this case, what we find is that the expected value of the periodogram, again, the periodogram is an estimator, the expected value of the periodogram, and then I think I was using a notation. Oh yeah, I need to give the, specifically with some t here for our frequencies, then this thing is going to tend to fx omega, which is just, as we noted from the Wiener-Khinchin theorem, h from minus infinity to plus infinity of kx h e to the minus 2 pi I omega j h, no j, omega h. Oh, I put a j in my notes, but I don't want a j there because now we're tending towards some limiting omega, right? Like I said up here in gray. Right, so what do we have? We have simply that, we're going to tend to the spectral density as long as we just finagle the omega j's so that they actually tend to something, because otherwise it would just go to 0, right? If we just fixed j and then took t to infinity, then omega j would tend to 0, and that would be really boring because then we would just have the spectral density at 0, which is not overly interesting, I think. Anyway, right, so we got that. Oh, yes. And then going furthermore, by absolute summability, right, of kxh, we have something else. We have that, therefore, we have that c can equal the sum h from minus infinity to plus infinity of h. Oh, that's right, the strength. I was going to say, this isn't the condition I want. This is a stronger condition. Let me write this sentence better after I write down what I want. Not by absolute summability. What I'm supposed to say is strengthening absolute summability to, and then get rid of that therefore. Make sure the English is right here. So if we strengthen the idea of absolute summability, remember absolute summability just says the absolute sum of kxh is going to be finite. Well, now I'm multiplying by an h in absolute value, so that's just making it, well, harder to get that summability condition. We need kxh to decay faster. So the point is that under a stronger condition on the autocovariance, we get that the covariance between the discrete cosine transform at some omega j and the discrete cosine transform at some omega k. Remember, because of symmetry, the sign isn't really there. Like a lot of times I'll write this as just a discrete Fourier transform like I did over here. But by symmetry, there's actually it's actually a discrete cosine transform because of the fact that the autocovariance is an even function. So anyway, the idea is that the coefficients, the discrete Fourier transform at two different frequencies, what's the covariance here? Well, if they're equal to each other, we're going to get something that looks like the spectral density at J over 2 plus some kind of epsilon t, which I'll mention in a second. Otherwise, we just get an epsilon t. And this is omega j equal to omega k, and this is omega j not equal to omega k. Right, so what's going on here? Well, again, the variance of the discrete cosine transform is the expected value of the squared discrete cosine transform. That's going to get us right back to the idea of the spectral density that we did up above here. I mean, it's basically kind of the exact same thing that we were doing. And the idea, though, is that it's going to be the spectral density. Again, there's like a 2 floating around here. But there's also going to be an epsilon, which is going to be an error term. So here, I should say where epsilon t is an error term such that the absolute value of epsilon t is bounded by c over t, where this c here is the same c that I wrote up here. So depending on how quickly the autocovariance goes to 0, the smaller this summation will be, and the smaller the error term will be. The idea, right, is we're trying to get down to some statistical notion of what's happening with our periodogram, but also very closely related to that, our discrete cosine transform, and ultimately how we're going to estimate the spectral density. So roughly this means that we have, this thing has a, no, never mind. It's just, it is what we have here. And as t gets big, the error term vanishes, right? So the error c here, it's also worth noting, note c, not a function of t, which is good, because what that means is as the data size gets larger, the error term shrinks, and that we're just going to keep dividing by a bigger and bigger number t. So what does that mean? So furthermore, so if xt is just white noise, well, what happens if it's just white noise, right? In this case, the spectral density is constant. Basically, then fx omega is just going to be sigma squared for the entire any frequency. And what this means is that in the limit, as t gets really large, right, because we're still dealing with a finite amount of data, and as our data size goes to infinity, we find out that the discrete cosine transform at any given frequency will converge in distribution to a normal distribution with mean 0 and variance sigma squared. Oh yeah, no, of course, we're computing the covariance here. I was like, wait, shouldn't it be that we're tending towards sigma square? Yeah, this is the variance we're getting out here. Sigma square divided by 2 for the covariance that I calculated above. This also happens for the discrete sine transform. And furthermore, these two things are going to be, well, and I'm going to say IID in the limit. Is it IID or just uncorrelated? I'm going to remove IID and just say uncorrelated. Probably if it's a Gaussian white noise process, then it's going to be IID. But in this case, I'm just going to say uncorrelated to be safe, even though I think the answer might be IID. The point is that the covariance here goes to 0 as t goes between two different frequencies. So ultimately what I'm going to get is all of my discrete cosine and discrete sine transforms should look like one giant multivariate normal distribution that completely has a diagonal covariance matrix. So there's no correlations between these things in the white noise case, right? This is all in the white noise case. Anyway, right, so we got that. Oh, good, we're coming right down to the end of this section. Therefore, since the periodogram, sometimes I feel like I'm just kind of like running around randomly, but there is an ultimate goal here, right? And what we're getting at is that the periodogram is going to be the sum of these two things squared. And when I sum up two squared random or normal random variables, I get something that's going to look like a scaled chi-squared random variable. Since this is true, what we have is that 2 divided by sigma squared times I omega j is going to converge in distribution to a chi-squared distribution with 2 degrees of freedom, which is a lot like what we talked about in the previous part about ANOVA, saying that there's 2 degrees of freedom associated with each frequency in the periodogram. So this is pretty cool because now we have some kind of, what we have is we have some type of limit theorem for what the limiting behavior of the periodogram should look like. Again, this is under white noise. Just to emphasize that we're still assuming that we have white noise here. Now, in general, we get a theorem. For, I think we need a linear process. For a linear process, xt equal to the sum, in this case, we'll take j from minus infinity to plus infinity of psi j omega t minus j. So it might not be causal. Note, might not be causal, but we do need the psi j to be absolutely summable. We need, in this case, WT, IID, white noise. Not necessarily Gaussian in this case, because by the central limit theorem, we don't need Gaussian white noise to get this convergence and distribution. But we will need IID noise. That's right. Oh, don't put the comma in yet. With variance sigma squared and with kxh such that we have this stronger summability condition, which is h from minus infinity to plus infinity of absolute value h, absolute value k, x, h. So again, we need the auto covariance function to go to 0 fast enough to make this happen. Now this does happen, right? If we have a moving average process, well, the auto covariance function vanishes after a finite number of lags. So that definitely is strongly summable like this. If we have an AR process, we know that the auto covariance function will decay geometrically to 0, which will also give us a nice absolutely strong summability condition here. So for ARMA processes, we're good. We're done. If we have a periodic process, it doesn't work so well. But for all the nice ARMA models that we've been worrying about for this entire course, this condition holds. So maybe I'll just write that in the margin just so you can see it. Holds for ARMA PQ, which is great, because that's more or less the only thing we've been talking about in this course the whole time are ARMA models, and this works for ARMA models. Okay, so let's continue this theorem. Then for any sequence omega j t going to omega, I think I used j here, omega j, we have jointly, so this is another keyword, jointly, that 2, let's see, yes, 2 times I, the periodogram, omega j to the capital T index divided by the spectral density tends in distribution to a chi-squared random variable with 2 degrees of freedom, assuming, of course, that f omega j is greater than 0 for all j, let's say, equal 1 to m. Oh yes, I should highlight that. What I meant by jointly is that this is a joint convergence and distribution for, say, omega 1 through omega m. So again, in with random variables, you could have convergence and distribution of one random variable in distribution, or you could have another one. In this case, they're jointly converging at once. So it is good to just be aware of that aspect of it. So what it means is that for all the frequencies, in some sense, or a discrete number of frequencies, we would have this joint convergence and distribution to a chi-squared random variable with 2 degrees of freedom. So that's kind of neat, because again, the numerator is an estimate, the periodogram. The denominator is an unknown function, the spectral density. I want to say spectrogram, but that's not the same. There's so many different things to keep track of here. Okay, so we have one final conclusion. The question that we always want to ask ourselves is, why do we care about the formula in the big blue box? And the reason is, so again, why is this interesting? Always a good question to ask in any math or stats class. It's interesting because we can construct a 1 minus alpha confidence interval for the spectral density That's kind of neat. Okay, what would that look like? Well, this is at some, well, let's just say for some frequency omega, not factorial, just exclamation point because I'm excited about it. And what it would look like, right, is to just rearrange this convergence and distribution equation above. And what we would end up with is something that looks like 2 times the spectral, or not the spectral density, 2 times the periodogram at some frequency of interest. I guess here, okay, I'll write it like this. And we're going to divide by chi squared 2, 1 minus alpha over 2. And this is less than or equal to the spectral density at omega. And this is less than or equal to 2I omega j t divided by chi squared 2 alpha over 2. And this is for some chosen frequency, which is approximately omega. I mean, I guess what we would want to do maybe is try to pick the omega j that's really close to omega. So again, if I had t as a power of 2, because I like powers of 2 because the FFT is really fast, but if the frequency I'm interested in is 1/3, well, I can't get 1/3 by having a denominator that's a power of 2, but I can get something that's really close to it. And that's the point, is that outside on the left and right hand upper and lower bounds here, omega j is the closest discrete frequency that I can get to the desired frequency I want. So again, the easy answer would be like if I had 1/3, that's a natural frequency we might be looking for. Oh wow, my camera died a while ago. All right, so I wasn't paying attention and I realized that my camera actually had died and turned off because I was so intently focused on all of this. So we'll just wrap up what I was saying. And what I was saying is that here we have a nice confidence interval for the spectral density. And this is really nice because what it tells us is that if I can estimate my periodogram at a bunch of discrete frequencies, omega j's, then I can estimate what I think the true spectral density will look like at some given frequency omega. And assuming the sample size is large enough, I can find an omega j that's really close to omega. And I can use the chi-squared distribution to get upper and lower bounds here on the spectral density. And that's great because now we can get a sense of what the actual spectral density looks like in some statistically valid, asymptotically valid way. All right, so that is more or less everything I wanted to talk about today. We did a lot of different statistical methods. We talked about how to use basically all around the same idea, which is how to use the periodogram to estimate the spectral density, right? We said, well, we can do that. And not only that, we can, in the limit, get a nice confidence band for the spectral density. We can also think of this as an ANOVA problem mathematically, even though in practice we wouldn't actually want to solve this as a linear system of equations because it would be a giant system of equations and that's never a good time. Going forward, we're going to do a little bit more with estimation of the spectral density because there's a lot more that we can talk about with respect to spectral methods. And we'll be doing that in the next lecture as well as looking at some R code because you can do this type of estimation in R. We did this a little bit in the last lecture, but we can do it with more sophisticated functions. I was doing it manually in the last lecture using the FFT function to show you what's happening, but we actually can use some real built-in functions that will do a lot more for us. And all of that will be coming up in the next lecture. So I will see you there.